Hey folks, thanks for taking the time to watch this presentation. I'll be talking about some work that we recently did that develops theory that explains topographic roughness on forest floors, and then uses that theory and topographic roughness as a metric for estimating the sediment flux due to tree throw. This is work that I did with Brian Unitas and Doug Edmonds at Indiana University, Bloomington, and was funded by the Environmental Resilience Institute. So I'm going to give you a brief overview of this work that we recently published. So if you are interested in learning more of the details about this work, I encourage you to go read this paper in GRL. So in moderate relief and forested settings, there are two classes of processes that are operating on hill slopes. The first class are creep-like processes. These are the processes operating within the soil mantle that chronically rearrange and create and collapse porosity, which leads to bulk downslope sediment transport. These include bioturbation, freeze-thaw, and true rheological and granular creep. In contrast to the creep-like processes, we have episodic processes, and in moderate relief settings, the only episodic process we have operating on hill slopes is tree throw. And tree throw is the sediment transport process that occurs when a tree falls, uproots soil and sediment with the roots, leaving a hole where the roots once were and depositing sediment adjacent to the hole, creating a pit mound couplet. We typically relate the volumetric hill slope sediment flux due to creep-like processes as a linear relationship with the land surface slope, and that linear relationship is modulated by a rate constant K, which we call the topographic diffusivity. I want to emphasize that the topographic diffusivity is fundamentally a rate constant that incorporates much of the uncertainty with regard to the sediment transport process. There have been many efforts that attempt to unfold and quantify the hill slope diffusivity over the years. I want to highlight one recent example from Paul Richardson in 2019, where he takes a global compilation of topographic diffusivity estimates and plots them against different environmental variables. What I want to show here is that for any single value of an environmental variable, estimates of hill slope diffusivity span over 2 orders of magnitude, just illustrating that quantifying and estimating values for the hill slope diffusivity remain a challenge for our community. Tree throw, on the other hand, is a no-doubter. You can go out in the woods, you find a hole and a pit, and you say, yup, sure enough, the sediment must have come from this pit and is now in this mound. You know how much was entrained, and you know how far it traveled. So those are two critical ingredients for understanding the sediment flux due to the process. And many folks have quantified the sediment flux due to tree throw, and they typically use an equation like the one I'm showing in the middle, which writes the hill slope sediment flux due to tree throw, Q sub TT, as a product of the tree throw production rate, P, times the volume entrained, times the average travel distance. Well, we can write that expression simply. I argue that actually constraining values for the tree throw production rate is pretty difficult, and that's because tree throw is driven by extreme atmospheric events, so either strong winds or heavy snowfalls. And the recurrence intervals for extreme atmospheric events can be long relative to human timescales, which makes quantification by direct human observation difficult. The other critical thing about tree throw that I want to point out is that it roughens the hill slope. So in figure C and D here, what I'm showing are two slope maps from two different LiDAR data sets in southern Indiana. Each one of those individual pockmarks is an individual pit mound couplet that has very clearly roughened the surface. The other thing I want to point out about tree throw is that it's consequential. And it's consequential because it suddenly inverts any soil depth varying characteristics. This is critical for understanding geochemistry. It probably modulates the weathering rates, and it's critical for mobilizing the coarse grains into the landscape. So the cumulative hill slope sediment flux in these settings would simply be the sum of these two processes. I want to point out, though, that we don't know either of those two rate constants, K and P, but for the rest of this talk, I'll demonstrate that the topographic roughness, which I emphasize is a measurable topographic variable, reflects the relative magnitudes of P and K. So from that topographic roughness, we can get relative magnitudes of these sediment transport processes. In order to do so, we had to develop an analytical solution or an analytical expression for the expected topographic roughness on a hill slope. To do so, we cast it in the following way. We recognize that pit mound couplets and tree throw are the only processes in these settings that roughen the landscape. And once a pit mound couplet exists, it is then subject to reworking by all creep-like processes. And features that are subject to reworking by creep-like processes evolve by a linear diffusion equation, which we've shown here. So we expect that the topographic roughness then scales with the ratio of the tree throw production rate to the hill slope diffusivity. In order to achieve an analytical solution, we first achieved an analytical solution for the diffusion of a single pit mound couplet, and that gave us a time series for how the variance of a single pit mound couplet varied through time. The mathematical steps that we did to do that are these two steps here, where we first analytically solve the diffusion equation for a pit mound couplet in wave number domain. So that's via the Fourier transform. And then we recognize that while still in wave number domain, we can use Parsifal's theorem, which is related to the variance of a signal. So when you do that, you get this expression down at the bottom, where the topographic variance of a single pit mound couplet declines with time with some nonlinear relationship through time. What I want to point out about this expression is that all the variables labeled in black are topographic variables related to the pit mound couplet geometry, which we've not explicitly discussed here, but is laid out in the paper. Variables labeled in red are the topographic diffusivity and time, which we don't necessarily know. So I just want to reiterate that this is a theoretical expression that yields the nonlinear decay of topographic variance of a single pit mound couplet. The topographic variance of an entire hill slope is simply the sum of all contributions from all pit mound couplets weighted by their age. So that amounts to a convolution, which I've shown here. The convolution is somewhat messy, so I tried to graphically represent that down below. Convolution involves convolving the tree throw production rate, which is some noisy signal through time. In this case, I'm showing a white signal. That's convolved with the variance decay by topographic diffusion, which is the result from the previous slide. When you convolve those two, you get a result which is some noisy time series of topographic roughness. And for the purpose of this work, what we were interested in was the mean or the expected topographic roughness. So we solved that convolution for the expected topographic roughness. And when you do that, this is the result that you get. So the expected topographic roughness is equal to a bunch of variables that relate to the pit mound couplet geometry, multiplied by the ratio of the mean tree throw production rate to the hill slope diffusivity. That result is not necessarily surprising, and that's sort of what we forecast a few slides ago. But you would expect hill slopes with more tree throw to be rougher and hill slopes with higher diffusivities to smooth out pit mound couplets faster, and you'd expect those to be smoother. But this result is significant because it was theoretically derived. We check our theory against some numerical experiments where we randomly create pit mound couplets and then diffuse them through time. What I'm showing in figure A is just a numerical surface from one of these experiments. And in figure B is the time series of topographic roughness for 100 numerical experiments. The theory is shown in red, so the theory matches the numerical experiments. Ultimately, what we're interested in for this work was the ratio of fluxes. And so in order to do that, we rewrite expressions for the fluxes due to these two processes. I do a bunch of algebra, which I'm not showing here, and then I form this ratio. And again, that ratio is the ratio of the sediment flux due to tree throw versus creep-like processes. And when you do that, you get this result. I want to emphasize that in this equation, there are no red variables. And throughout this talk, I've tried to highlight the variables that are unknown rate constants in red. So this expression includes only measurable topographic variables that we can get from high resolution topography. So R is a valuable tool that we can map across wide areas and have an understanding of the relative contributions of different sediment transport processes. So we did that in southern Indiana using a high resolution topographic data set at 0.76 meter resolution, that's 2.5 feet. In order to calculate topographic variance, we first ran a high pass filter over that data set, which yielded surfaces that look like the one on the right in figure B. The high pass filter, so that just illustrates that the high pass filter reveals only topographic roughness and removes the valley scale topography. So this figure contains much of the results from this work. We measured topographic roughness and calculated R on nearly 2,000 hill slopes across Brown County. What I'm showing on the left is a hillshade from Brown County. Each of those dots is a location that we calculated topographic variance from a hill slope, and they're colored by the value of variance that we measured. We see in figure B that topographic variance shows a modest relationship with slope. And then in figure C and D, I'm showing cumulative probability distributions for the topographic variance and the land surface slope. The color of those lines correlate with the rose diagrams below. So the darker lines are generally east facing and the brighter lines are west facing. If you squint your eyes, you can see a trend that we generally have more topographic variance on east facing slopes and less topographic variance on west facing slopes. I'm going to talk about figures E and F here in detail. We note that R varies between 0.2 and 0.35, which corresponds to about 11 to 18% of the sediment flux. We also point out that there is a modest correlation between R and the wind speed direction and magnitude. So I want to bring your attention to figure E. In each one of those violin plots, there are green circles. Those green circles represent the average value of R. And I want to point out that they also form a circle that appears to be offset from the center, indicating that east-facing slopes have a greater percentage of the flux driven by tree throw. That correlates with wind speed, which is shown in the rose diagram in figure F, where the frequency in which the frequency of wind direction is shown by the gray bars, so it blows most frequently in the northeast direction, and the magnitudes are shown by the violin plots. R is somewhat lower than we expected. However, we note that tree throw is limited by tree growth rates and spacing. And we also emphasize that our eye is drawn to the roughest parts of the landscape when we sort of think about this process. Okay, so for the next 3 minutes or so, what I want to do is sort of tease the work that we're doing right now, which asks, what else can we learn from topographic roughness? So topographic roughness is a random variable, and it's a random variable because it's driven by stochastic and noisy processes. The stochastic and noisy processes are the extreme weather events that drive tree throw. What I'm showing here in figure A, B, and C are just 3 different hill slopes that have 3 different roughness values. And I want to reemphasize that we measured roughness on 2,000 hill slopes, so we have a decent idea of the probability distribution of topographic roughness, shown in figure D. So we're currently asking, what other information can we learn from the distribution of topographic roughness? Well, we've already shown that through this convolution, we have developed a relationship between the expected topographic roughness and the mean tree throw production rates. The work that I'm currently doing, I also demonstrate that there is a relationship between the variance of topographic roughness and the variance of tree throw production rates. I hope it's not too confusing, but I've exchanged gamma for topographic roughness. I did that because when you start talking about the variance of the variance, things get confusing rather quickly. So ultimately what we're after using this is we want to develop a probability distribution of tree throw production rates given the information that we have in topographic roughness. So we know that there's a relationship between the mean topographic roughness and the mean tree throw production rate. We also know that there's a relationship between the variance of topographic roughness and the variance of tree throw production rates. So we cast this problem in this way. Tree throw is driven by an exceedance probability problem where tree throw occurs when the driving force, that is, in this case, the drag force imparted by wind, exceeds a resistance or strength force provided by the trees and soil. So what we're illustrating here is that the overlap between those 2 distributions determines 2 things. It determines the, I think we might have lost power. I wonder if this will keep working. It determines the, it determines the probability distribution of tree throw production rates, and it determines the statistics of topographic roughness in the landscape. So using that logic, we're able to to use the rules of marginal, joint, and conditional distributions in the following way. There's a lot here. I'm going to try to get through it in, 30 seconds. So we note that the overlap of driving, so driving forces provided by wind and drag forces, and the distribution of tree strength and resistance forces creates a conditional distribution. That is, what is the probability of X number of trees falling given a driving force? From the conditional distribution, we can create the joint probability distribution of true throw production rates and driving force. And then once you have that joint probability function, what you can create is the marginal distribution of true throw production rates. So what I'm showing here are three different estimates of true throw of the probability function for true throw production rates for different hill slope diffusivities and a simple Weibull fit. I am slightly over my time. So if you're interested in this, please ask questions. These are some conclusions, but I'm going to end here. Thank you for your time, and I look forward to seeing you in virtually or in person in New Orleans.